Just you can see.
Angle.
Yeah, is it audible?
The distance between the upper and lower blades is known as the blade or knife clearance. Knife clearance is essential for proper shearing and is modified for different material thicknesses and strengths. As the blades come together and contact the workpiece, they partially penetrate the material. This builds up opposing forces in the stock. A crack or tear called the slip plane then develops on both sides of the material, separating the stock. The shear blades typically penetrate the stock no more than 1/3 of the stock thickness before the slip plane occurs. The exact amount of penetration varies with material hardness and knife clearance. On most shears, the upper knife is aligned at an angle to the lower blade of between 1/2 and 2.5 degrees. This angle helps concentrate the shearing force in the exact area of blade engagement between the two knives and starts the fracture on a straight line parallel to the surface of the knives. This inclination also causes the upper knife to move away from the lower knife during the shear. This ensures that the sheared workpiece, called the drop, will not become wedged between the two blades.
Yeah, okay.
Element has been part of.
Is it clear?
Yes.
Awesome. So maybe when we will go detail, like the all the rolling, forging, and extrusion, maybe that time we can see videos, like the proper videos with some, like maybe when the hot rolled product is coming, maybe that one I will show you. Maybe yesterday I was looking that one. Maybe somewhere I visited some companies, big companies like Jindal or maybe some other companies. Maybe I want to show that one actually, but I could not find that video. So that's why I am showing this one. Maybe next time when we have the proper, like rolling, forging, extrusion, when we'll go like deeply, maybe at that time I will show you. It will be much more better for you, right? So then one more also, maybe few students, one student I think, just yeah, Nihar asked about the how do you see India's future with automation in the assembly sector, given that our population is increasing exponentially and the Make in India policy is basically to create more jobs. Yeah, this is like what I'm saying here. If you are talking about the Make in India policy, especially we like in India, but if you are talking about only focus on the automation, maybe you can focus on in that particular area. But according to my knowledge, because whenever we are writing any kind of research proposal also, we are focusing on Make in India. Okay, so why we are talking about Make in India? Because everything we have to do indigenously here. Okay, that is much more important here. So basically when we are talking about in any university or any institute, normally we are segregating the students, for example, in three ways. One is if some people they want to go for research, they can go for, or they can think for MS or maybe PhD. And the second one, the students they want to do immediately job, for example any kind of company they want. And the third sector, what you are talking about, the Make in India, these people we are focusing on how they can develop by themselves to become a proper or maybe good entrepreneur, right? So in that case, if you will see all the manufacturing hub, for example, what we are talking about, global manufacturing hub we are trying to do, or we are trying to become as our country India. Okay, so and we are also thinking to become, maybe after some years we'll be the leader in innovation. Because if you'll see in USA, in one zone actually you will find all the Indians, and maybe in one zone you will find all the Chinese, because these two countries, if you will see globally, we are dominating everywhere. Okay, but we do not have infrastructure here, maybe if you will see in the last years. But nowadays we are improving. For example, now you can see in food sector you can go, apart from the manufacturing also I'm taking in food sector, we are exporting a lot of foods to other countries, right? So similarly, if you are talking about manufacturing also, so we are focusing on now, like the smart manufacturing, now the industry 4.0, that one also we are coming up. Then how we will enhance the productivity, that is important. If you will go to the Gujarat, Rajasthan, that side, they are much more focusing on the entrepreneurship or the companies. Just only they are going to the college and earn some degree, and after that they are immediately they are starting up their startup or maybe business, right? And also at the same time also we are focusing on, if you are aware of that one, the product development. Okay, so because we are now in a in a lower level now, for example, student or maybe a fresh teacher probably. But when we have some development of the product, then maybe later stage we can think about how we can enlarge. But in research, if I will tell about, we are doing laboratory scale initially, then we are going to the pilot scale, then we have to go for the industrialization. For example, what you are doing now, product development, this is laboratory scale. Then you are preparing a prototype, right? Then after that you have to go for the industrialization. So these are, and if you will see only automation, you cannot, this is a small word, automation. For example, if you will see the oil industry, how much oil we are importing from outside? Almost, I think 75% of oil we are importing from outside. And if you will see the energy efficiency also, okay, and nowadays we can see the software development, how we are making. Okay, so if globally we'll see we are much more ahead when we are developing the software. So you cannot tell only the automation in one field, but if because Make in India is not only for automation, if you will see overall in a bigger perspective, you will find several areas, but where you are actually suitable or you are focusing on in that particular area. Okay, so I think Make in India will have a much more impact in future, or also now it is already started, because whenever we are also submitting, because I will tell about my experience when we are submitting some project proposal, so we are focusing on Make in India. Okay, because if we'll focus, then probably government will give you some fund, or maybe, for example, if you are starting some initial business, let's say, so government is giving you funding or loan, what we are telling in the local language. So in that case also you can go. There is not an harm. Okay, is it clear?
Yes, sir.
Yeah.
It's clear.
So we have discussed up to that slide. Then we have to go for the metal forming. So again, I put here a few comments what we have discussed in the last class. So the last group manufacturing process in which the plastic deformation is used to change the shape of a metal workpiece. So we define two processes. One is plastic deformation and one is elastic deformation. Of course, we are covering here the plastic deformation because we are preparing the metal forming. So here what we are doing, we are changing the shape, whatever the schematic diagram I have given in the previous class, the rolling, forging and extrusion. So we are changing the metal piece, okay, with the help of the die. Whatever the die size you have, based on this you have to change. And the tool usually called a die applied the stress that exceed the yield strength of the metal. Probably I will show again maybe stress strength diagram, because these are already you have studied in your strength of material, or also you have studied in material science and technology. So also I will just put a recap of the stress and strain diagram. The metal takes a shape determined by the geometry of the die, whatever the size and whatever the looks of the die. Similarly, you have to do that one, or you will find that one, or you will create that one, right? For example, if you will see maybe in composite materials, I think I have talked to you about the powder compaction. Like, we have some die and the punch. So if you have some powders, you can press it from both the end, okay, or from both the side. The moment you will press it, then you will find or you will prepare a tablet there. Okay, so that means this like a forging kind of thing. Okay, so we have probably in the lab, you have the the press or the hydraulic press, what we are talking. And the stresses to plastically deform the metal are usually compressive. So normally what we are generally we are talking about, these are compressive. But apart from the compressive also, because if you will talk about the compressive, the examples are rolling, forging and extrusion. We have what we will study in detail. These are, that means you are making the compressive strength, or you are applying the compressive strength. Apart from the compressive strength also, sometimes we are using the tensile stress, and also sometimes we are using the tensile and compressive both, and sometimes also we are using the shear stresses, whatever we have discussed in the last class with some schematic diagram. Okay. Yeah. So there are some material property in the metal forming, because you cannot tell that, because what I have shown in that video also, some portion in the video, it was actually emphasized that how you will cut, because the moment you will cut it, because this is similar to cutting. Okay, but here it is two things are there, because whenever you have the soft material, because high thickness but the soft material, so that means it looks red, like that's why I give an example of the blacksmith. Whenever the blacksmith, actually what he is doing is putting the metal into the fire, then when it will become the soft or maybe red in color, then he will hammer it, then he will change. These are we call a manual operation. But when it is done by automated, like hot roll product is coming from the long far, maybe 200-meter far or maybe 300-meter far, it is coming. Then suddenly when they need small pieces, so they have to cut there, or they have to stop there. Okay, because they cannot keep it very long, because they do not have any option to otherwise they can roll it. They can also roll it, there is a possibility. But if this is very thick, then you cannot roll it. If this is thin product, then you can roll it. And after rolling also, you have a option that you have to coat it, because you know some materials it can be corroded, so that if you have to coat it or maybe you have to paint it, then only you will transport from somewhere, right? So the material property also you have to think about. One is low yield strength and is high ductility. Then the main thing is here, these properties are affected by the temperature. Okay, so the temperature is much more important here. But apart from this also, the corrosion, this kind of factor also it will come, but only whenever we are talking about the metal forming, because we are putting inside the high temperature, because we are making it very soft, then only we can change this shape. Without increasing temperature or without making some softer material, you cannot change this shape. So while the ductility increases and the yield strength decreases when work temperature is raised. So that means the moment you will increase the temperature, of course, we will also define what kind of temperature zone is available, or what kind of metal working possible with the help of the temperature or with respect to temperature, right? And the other factor also, we have to also study step by step the strain rate and the friction, because whenever you see the video, in that video also when it is cutting actually, so you will find some friction there. Okay, so how it will affect also, that also we will study strain rate and the friction also, right? Is it clear?
Yes, sir.
Okay.
Yes.
Yeah. So next one is the material behavior in metal forming. How actually when you will changing, or when you will forming some metal, or when you have the raw material, so you are converting with a different shape, how actually it will behave in that case. So also we have a the title also, like the metallurgical aspect, or the the mechanics of the metal forming. That also we will go step by step. Okay, so if you will the schematic, if you will the graph here with the stress and the strain, so this one is the linear region or the elastic region in the beginning. Okay, so in the first part, and the second part we have the plastic deformation here, and the third one we have the strain hardening here from here to here, and the next one we have the fracture or the necking portion, what we are telling. Okay, and the total from O to E dash, if you will go to here, and this is known as the true stress strain curve, right? And if you have the sample, these are I think already you have done in your strength of material. So when you are expanding the material, so what you will find from here, so you will find a fracture here, so that means this point. Okay, and this portion from here to here, whatever we have the here, so you will find some necking there. Okay, so step by step. For example, if you have done maybe in childhood, maybe some kind of material, soft material, because metal we cannot do by ourselves manually, we cannot do. But if the softer material, sometimes we can stretch, and sometimes it will detach from there. Okay, but probably we could not predict there at that time, because we were not aware of how it is happening, or how the mechanics actually behind this. So probably when you have studied in engineering, then at least you will understand that how actually it is happening, what is the steps actually. So when we are trying to do, when the metal we are stretching, or when we are for example pressing, how this is happening or how this is changing. For example, now you can see here the metallurgical structure or the microstructure. If you will put small sample in scanning electron microscope or maybe the optical microscope, you will find the grain boundaries. It will it will be enlarged there, because you cannot make it in proper zone, proper position. So maybe I will also show, maybe in the next class, or maybe next class, how the microstructure is changing. In schematic, I will show you how it is changing from, for example, in here, and maybe in here, and maybe again here, in here. Okay, so these are the stress strain diagram. Yeah, so again, when we are talking about the stress strain diagram, so again we have to understand that how actually this relation happens. So the stress strain relationship beyond the elastic range, whatever I told in the previous graph, you have the elastic zone here. Okay, so in the beginning part, 0 to A, for example, here. Then after the elastic zone, you are finding the plastic zone or the plastic deformation zone. So we are talking only about here, only the plastic deformation. We are not considering anything of elastic deformation. Okay. So the stress and relationship beyond the elastic range, assuming no unloading at any time and anywhere. Okay, so that means whatever happening, the unloading part, this is already happened in the elastic zone. So we are not assuming anything there. So the plastic region of stress strain curve is a primary interest because material is plastically deformed. Okay, so why actually we are considering there, because in our case, whenever we are talking about the material deformation, we are only thinking of plastic deformation. okay, or maybe the mechanical working, what we are saying. So in plastic region, the metal's behavior or the material's behavior is expressed by the flow curve sigma equal to k epsilon to the power n. Okay, so this equation I think you have heard in strength of material. If not, just you can find out this equation sigma equal to k epsilon to the power n, where k equal to the strength coefficient. Because why we need this strength? Because you have to make it plastic deformation. That means you have to apply such a strength so that it will deform, right? And the epsilon is known as the maximum strain, because you have to go for the maximum strain, then only it will happen. And the n is known as the strain hardening exponent or the strain hardening you can call. And the stress and strain in flow curve are the two stress and the two strain, whatever I have shown you in the previous graph also. If you will see from here, from O to E dash, not to the E, because whenever you are going to the E, that means you are going to the fracture side, you are going to the necking side. Okay, that means you are trying to make it deformation. But the moment you are not trying to go for the deformation, so you will go to this zone. So this is known as the true stress strain curve, true stress and true strain curve. Okay. So this is known as this equation known as the flow curve. So if we'll go to the flow stress, how actually it will happen and what should be the equation? This is also the similar equation, but for most metals at room temperature, strength increases when deformed due to the strain hardening. So what is known as the strain hardening? Because you are giving some strength to that metal or to strength to that alloy, right? So if you'll see the schematic diagram here again, the same thing, but only I made it smaller. So this is the true stress in the y-axis and the x-axis is true strain. Okay, so if you want to find out the flow stress, what should be or how we will do that one, and what is the basic definition of the flow stress? Instantaneous value of stress required to continue deforming the material. So that means the moment, for example, if somebody is standing there, okay, so that means we are pushing. The moment we are pushing in a such a limit or in in the maximum force, then only the student or the person will go front. Okay, so that means he will walk. But the moment we will press, but he'll again opposing something, then we cannot make him press because he cannot go to the front again. So that means we are applying in a continuous stress so that this material is going to deform. If we'll make it stop somewhere, then it will not work because it will not go to the necking or the fracture in the last point. Okay, so it will stop somewhere. So here we are mentioning this y equal to k epsilon to the power n, where the yf equal to the flow stress, that is the yield strength as a function of strength, and the k is known as the strength coefficient, whatever I told in the previous slide, and the the n equal to the strain hardening. Okay, and if you have the flow stress, for example, if you are finding the flow stress here, for example, this one, okay, and you can find the flow stress also here, you can find the flow stress because from here to here there is a big zone or the big area. But how we will make it, because you cannot tell this one is the flow stress, you cannot tell this one is flow stress. So what you will do, you have to take the average of the flow stress. So that is the correct flow stress you can tell, or you cannot tell that for example, somebody will tell why you are not taking here. If somebody is telling that in this point only you have to find out the flow stress, then you can take only this reading. But if somebody is telling only you can find out the flow stress, so you cannot take every point. So you have to take some points, then you have to take the average one. So the also called the mean flow stress is the average value of stress over the stress strain curve from the beginning of strain to the final value that occurs during the deformation. In other words, determined by the integrating the flow curve equation between 0 and the final strain. So that means if you take the integration of the flow stress curve, okay, in the this equation, but the limit you have to take from 0 to epsilon. Okay, so that means your equation or your integration you have to take from 0 to the final strain. Final strain is epsilon. So that means integration 0 to epsilon, then this equation you can put. So that you will find this yf bar equal to k epsilon n to divided by 1 plus n. So where yf is known as the average flow stress and epsilon is known as the maximum strain during the deformation. Okay, is it clear?
Yes, sir.
Okay.
Yes.
Yeah, so now we are going towards the temperature in metal forming. Of course, when you will, because now when we are studying the theoretical, normally, we are normally a board, but the moment you will see the the animation or the pictures, so you will find how actually this temperature is really it is much more important whenever you are doing any kind of metal forming. Sometimes we are very curiosity. When we studied, for example, any material you are just melting. Okay, and this melting, for example, maybe recently I was looking somewhere, that video I think I have shown you sometimes, the aluminum plate, the waste aluminum, they are putting just in a furnace. This furnace is not very accuracy or something. They were just putting the waste aluminum sheets or maybe the waste parts in the furnace. So after maybe 10 or 20 minutes, they were finding some liquid aluminum. So we were studying on like water and maybe these kind of things, but the metal also they are melting, and sometimes higher melting temperature metal also they are melting. And again this the molten metal they are just taking with the help of a cup, with a long stick, because you cannot go to very close to that furnace because high temperature is there. So they are putting, and they are just putting by hand in a, like some mold. So they will find that. But when you are going for the mechanization process or the automated process, you do not need to go there. Okay, so everything you have to control from the PLC, or maybe to some hard automation what we are talking about. Okay, so then you will find a different kind of based on the different mold you will find, because that demand from the customer, because the customer will tell that I will take maybe 1 meter by 1 meter piece. So what you will tell, because if you do not have mold, so you have to prepare the mold. I think in manufacturing you have prepared a sand mold, I think, if you remember your manufacturing lab. Sand mold you have prepared, then you have prepared some molten alloy, or maybe of course molten alloy normally we are making because the melting temperature will be lower, or maybe the aluminum normally. Okay, so that one you are putting in the sand mold, then based on that size you have created, then you are taking that, right? So any deformation operation can be accomplished with lower force and power at elevated temperature. Okay, so what is meaning of elevated temperature? So that means the chemical phenomena occurring at that particular temperature. For example, if you are considering water, so what should be the elevated temperature of water? So 100 degrees C. Okay, so that means it is changing from one phase to another phase. So at elevated temperature, n equal to 0, yf bar equal to yf equal to k. Okay, so at elevated temperature, we are considering this one. And for any metal, k and n in the flow curve depend on the temperature. Okay, so for example, you can see, I do not know whether you have done any experiment, probably last 2 years, of course, you have not done. Maybe in your, chemistry lab, maybe in first year, or maybe in your 10 plus 2, sometimes we are generally, the copper sulfate dissociation, normally we are doing in our, chemistry lab. So how actually from copper sulfate solution, how you are depositing copper and you are, deposited in a substrate, how you are doing. So that means you are dissociating the copper sulfate, but you are applying some voltage there and you are applying some current there. Of course, you have to do one. Either you have to fix it current, or you have to fix it the voltage. One you have to vary. Okay, so then from copper sulfate, the copper will come out and you will deposit in a anode, in a electrode or in a substrate. So here both strength and the Stern hardening, K and the N, are reduced at high temperature. So at higher temperature, something will happen. Then only you are going towards the plastic deformation. In addition, the ductility is also increased at higher temperature. So whenever you are, so that's why I told in the beginning that what are the material behavior you have to study. You cannot tell that for aluminum what is the material behavior, for tungsten the material behavior will be same. No, because both the materials property will be different, melting temperature will be different, all the properties almost you can say different. So you cannot tell, one is in the lower side and one is the higher side. Okay, so there are three temperature range in the metal forming process. So one is cold working, and the second one we have the warm working, and the third one we have the hot working. Okay, so can you tell, just have you heard about these three terms, cold working, warm working, and hot working?
So,
Yeah, so can you just tell with any any one line how to define this cold working, or what you are understanding from that? I have in the next slide I will show you, but if anybody, if you know, just you can share.
Deforming the body without heating the metal is called cold working, and heating it below the recrystallization temperature and deforming it is warm working, and going above the recrystallization temperature and deforming it to get the shape is hot working.
Yeah, great. Any other student?
Same definition, sir.
No, you have to tell na, same definition. No, you have to tell. You have to.
Sir, like hot working compared to the other two, cold working and warm working, works at a higher temperature where the deformation takes place, whatever metal we desire to produce.
Yeah, Amal. Yeah, fine. Thank you. So you can see, just I put a schematic diagram for you. So if you will see, you know, everything, you know, almost the recrystallization temperature. So if you'll see the schematic diagram here, okay, so the upper part, okay, so for example, yeah, somebody is telling, yeah, okay, fine. So I put a schematic diagram for you here. So if you have the upper part, it is hot working, and the lower part I put this is cold working, and the medium or the middle or in between the hot work and the cold one, we have this is warm working. So you know already the recrystallization temperature, but still I put one definition here. The recrystallization is a process by which deformed grains, because already you have aware of this one because you are already in third year. So I think you have studied in material science, and then also I do not know in other subject where you have studied this one. But the recrystallization is a process by which deformed grains are replaced by a new set of defect-free grains. Because whenever you are also, maybe I do not know whether I will teach you the recovery, recrystallization, grain growth. I do not know whether you know in the syllabus we have or not. Maybe I will try to put maybe one or two slide maybe in future, so that at least you will understand that what is recovery, what is recrystallization, and what is grain growth. Okay, how these three are interconnect to each other. That also maybe I will try to tell you. So here the recrystallization is a process by which the deformed grains, because whenever you are stretching or whenever you are applying force, that means some grains are actually, you know, deformed in that side, okay, or that situation. So what will happen? So that grains or that deformed grains you are replacing by a set of defect-free grains. So how we will get it? So that's why I told these three mechanisms are there: nucleation, growth, and the recrystallization. So that nucleates and grow until the original grains have been entirely consumed. So that means you have to keep in a certain zone, or you have to keep in a certain period, so that these deformed grains, it will nucleate again and it will form a defect free grains. Okay, so that is the meaning of recrystallization. So here you can see the recrystallization temperature we have taken here. So 0.4 time of the melting temperature. This Tm is melting temperature. Okay, so what you told both the students, the hot work, or maybe the hot working, when we are considering this, the plastic deformation above the recrystallization temperature, wherever the cold work is the plastic deformation below the recrystallization temperature. Okay, so here also when we are talking about the hot working, so the lower limit we have mentioned here 0.6 times of the melting temperature. Wherever the cold working, this is the maximum limit, okay, it is known as the 0.3 times of the melting temperature, right? So this is the basic meaning of the hot working, and warm working is in between the hot working and cold working, right? Is it clear? Yeah.
Sir.
Yes.
Yeah, great. So then only just I put one slide, like, you know, what is actually cold working and what are the basic like, you know, advantage of this one and maybe disadvantage of this one. Okay, but this depends upon the material. Okay, so maybe these are the common statements for the, or common advantage and the disadvantage of the cold working. So it is performed at the room temperature or slightly above, and many cold forming process are important mass production operation. Okay, so whenever we are talking about mass production, so you are also thinking about the cold forming, and the minimum or no machine is usually required. But you told about that we are not actually using the machines, okay, at that time, because just only we are making the cold working, and these operations are near net shape or the net shape process. So this operation, when we are talking about, these are known as the near net shape or the net shape process. So how to define the near net shape? So this term is given to a process that aim for the initial fabrication of a component to be close in size and shape to be finished product. So that means whenever you want to think about this kind of, or this shape and size of the product I want to produce or I want to prepare, so this is very close to that size. Okay, so that's why we are talking about near net shape, because in the normal like, you know, the English word we are talking about, this is accurate or maybe accuracy, or we are very going towards very close like, you know, shape. Okay, so in technical term we are talking about near net shape. Okay, and better accuracy, closer tolerance, and the surface finish. Strain hardening increases strength and hardness, and grain flow during the deformation can cause a desirable directional properties in the product, and no heating of work required. Okay, so what I told from the name onwards, this is cold working. But what is the basic disadvantage of this one? So I just separated from here. You have to understand which one is advantage and which one is limitation. So I just put in a bottom higher forces and power required, because you have to apply the power and the higher force, and the surfaces must be free of scale and dirty or the dirt. Okay, and the ductility and strain hardening limit the amount of forming. So some limitations are there. You cannot tell that every time cold working is best. The techniques also what we have discussed in maybe other or the previous subjects also. You cannot tell that all the techniques or all the technology what we are developing, everything is good. Somewhere we are finding or we are getting some advantage and some disadvantage, but based on your material or your process or your goal or aim, we have to apply the proper technique there, right? Yeah. So if you go to the worm working, so this is performed at above the room temperature but below the recrystallization temperature, and the dividing line between the cold warming and the warm warming often expressed in terms of the melting point. Okay, so normally basically what we have defined the cold working or the warm working or the hot working, this basically depends upon the melting point of that material. So this is 0.3 times of the melting point, where Tm equal to the melting point of the absolute temperature, and it lowers forces and power than in cold working, and more intricate work geometry is possible, and need for annealing may be reduced or eliminated. Okay, so the annealing, the heat treatment also, I think you have studied probably somewhere. I don't know the annealing, normalizing, hardening, and tempering. That also probably you have studied somewhere. If not, just you can go through maybe some books that what is actually annealing, what is normalizing, what is hardening, and what is tempering. Normally, four you can just remember, because this is the very beginning of other steps or other process. You do not need to remember, not necessary. So the last part is the isothermal forming, eliminates surface cooling, especially highly alloyed steel and titanium and nickel alloy. Okay, so that's why I put here one alloy, because you cannot tell that all for all the alloy you have to go for the worm working, or for all the metal you have to go for the worm working. You cannot go, depending upon the behavior of the material, depending upon the properties of the material, and depending upon the methodology or the process of the material, or the aim of the or the goal of the material. Then you have to choose what kind of process you are going for, or what kind of process. And also one more thing is the feasibility and the cost. That factor will come every time, because you normally when you are going for the, because I remember in composite materials every time some students they were asking about the cost. Of course it will come, because whenever you are starting some business or maybe some company or maybe some manufacturing setup, of course you have to go for the low cost, because you cannot go for the higher cost immediately. Okay, and the last one we have the hot working. So the hot working also, this is deformation at elevated deformation at temperature above the recrystallization temperature, and the recrystallization temperature equal to the above about one half of the melting point on absolute scale. Okay, in practice the hot working usually performed somewhat above the 0.5 times of the melting temperature, what I told in that schematic diagram. And also a perfectly plastic material, strain hardening exponent is zero, theoretical normally. Because another thing also, many times some students they're asking about, maybe last time also, I do not remember who was asking about, we know about the ANSYS, then sometimes the theoretical whatever we have studied, this is the fact. That same theory you cannot implement there, because when, for example, now we are looking, for example, the iron melting temperature, how much? Around 1539. This is theoretically, this is established. But whenever you are putting in a furnace, maybe you cannot make at 1539 you will find the pure iron, liquid iron you cannot find, because that depends upon that furnace system, that atmosphere, that the amount of the material. So it depends, it will vary, maybe 10 to 20 degree it will vary. So you cannot tell that 1539 will be the melting temperature of iron. Okay, so it will vary, so you cannot tell, but theoretically we are considering this one. So what are the advantages? The lower forces and power required, the metals become ductile, and the strength properties are generally isotropic, no work hardening of the part can be subsequently cold formed. Okay, so these are the basic, or maybe some, apart from this also you will find a lot of advantages there. And basic, what are the limitations? Lower dimensional accuracy, higher total energy required, then poorer surface finish excluding the oxidation, and the shorter tool life. Okay, so that means why we are calling here a tool life, because the moment you are going for hot working, so that means the material also, for example, if you are going for the the billet, the hot rolled billet, but at that time you are using the hot working, so whatever the tool you are using there, because it will contact with the high temperature there. Okay, so that's why the tool life will be shorter. Maybe in the last machining, I think we have discussed about the tool life. Okay, we have done some numerical based on this, I think, right? Is it clear?
Yes.
Yeah. Okay. So now only you have to tell me now only one question just I will ask you. Why we are going for hot working? I put the answer also in the next slide. Why normally, just you can guess why you are, what is the basic importance of the hot working.
Reduces the thermal stresses. Yes.
Reduces the thermal stresses. Yeah. Any other? Anyone? Just guess. You can. Whatever we have studied, maybe you can just guess one or two line or points. You can just tell. If not, also this is fine. Not an issue. Amal? No.
Sir, thinking, sir.
Yeah. Okay. Fine. Not an issue. Okay, fine. So I just put 2-3 points here. What is the basic meaning or the basic importance of the hot working? So the capability for substantial plastic deformation of the metal far more than possible with cold working or warmer. Okay, so that means if you can get something like substantially better. For example, let's say like maybe last time I have asked you one question: why actually we choose mechanical? Okay, so maybe like we can compare with the computer science or maybe from the chemical or maybe from the civil, that what is the basic importance, or why I can tell that no, mechanical is the best, or maybe normally we are calling this the royal branch. This is every time like popular. Computer maybe today it has demand, maybe tomorrow we do not know. But mechanical is every time like mechanical, civil, these kind of branches are every time. Maybe today is little decrease. This is worldwide. We cannot say only here we have in Chennai. Worldwide this is a little decrease. Maybe after 2 years again it will grow. Right. So the capability for substantial plastic deformation of the metal. Okay. So the next one we have the strength coefficient is substantially less than at room temperature. Okay, so what is the basic meaning or why we are going? And the strength hardening is exponent is 0, and the ductility is significantly increased. Okay, so these are maybe apart from this also you can write some other points also in other way or in other words also you can write. That is not an issue. Okay, so that's why any process or any technique whenever you are using or whenever you are doing or whenever you are creating, maybe when you talk about the Make in India also somebody was asking. So in that case you have to define why we are going for this one. Whether this is expensive, whether this is cheap, it doesn't matter. But you have to tell that, or you have to believe from by yourself that why actually I am doing for this one. That's why I asked in the previous class also why you have chosen mechanical as my brand. You have to decide. You have to define by yourself. If you have not defined, just only my parent they pressed me to just go to that mechanical or maybe civil, then I do not think it will be the correct answer, because you choose that one. Because in your degree your name will be there, no other person's name will be there. So you have to define. If you have not defined also, you have to define now that why you have chosen. If any negative things, that you have to avoid. If you have already entered to mechanical, if all the positive things will come out now, so you have to define that why I have chosen BTech mechanical, or maybe why I will go for MTech mechanical, or maybe MTech CAD/CAM, or maybe PhD mechanical. Okay, we have to define, right? So I finished everything. If you have any question, you can ask. In the next class, we will talk about the strain hardening. Okay. Yeah.
How does hot working reduce thermal stresses?